Recently in tutorial, I've been getting a few questions about where dot product comes from and sort of the fundamental intuition behind dot product and cross product. So this video is to give you guys a bit more of a solid intuition of the concept. Before we start talking about dot product explicitly though, let's talk about this physics problem, okay? So I have a force F and a distance D, both described by vectors, okay? I'm pushing this block with a force F, and I'd like to move it a distance magnitude D in the direction of D to the right, right? So I'd like to move it, in this case, 3 units to the right, and that's described by this vector D, okay? And now I might want to know, okay, I want to expend the least amount of force to move this block, this distance D. In which direction should I in which direction should I orient my force? Which direction should I push the block, right? And so it's pretty intuitively obvious. Well, if you want to expend the least magnitude of force, if you want to expend the least energy, then just move the block in this direction, right? Move the block push in the exact same direction as you want to move the block, right? Because then you can spend a smaller amount of force and a smaller amount of energy to get the block to that position, right? Whereas let's say I'm pushing this way, then the only part of this force vector, right, that's actually pushing the block to the right is the x component, right? We can break this down to two components, the x component and the y component, and the only component that's actually doing work that we want to do is the x component, f of x, okay? And so, and for instance, if our force vector was completely perpendicular to the distance vector, then we would do no useful work at all. We would not push the block forward at all, and we just waste a lot of energy, okay? So it's intuitively obvious that in this case, we want to maximize the x component of this force vector in order to transfer the most energy from the force vector to the block to push it this distance, right? But how do we quantify this? Okay, how do we quantify the fact that pushing it, up is a bad idea? Well, let's figure out a metric that can tell us how much of this force vector results in energy being transferred to the object to move it in this direction. So we know that if the force vector and the distance vector are both pointing in the same direction, then this metric will be high. This metric should give us a high value because this is good. This is the maximum amount of energy transfer. But if our force vector is orthogonal to the distance vector, if it's completely vertical, then our metric should give us a really low value. Okay? And so what's one function that we could use to describe this? Well, one function is the cosine function, right? So we expect a cosine to show up somewhere here. Because cosine, when the angle is 0, when the angle between the and we're talking about the angle between the two vectors, right? We're changing the angle between the two vectors. When the angle between them is 0, cosine is maximum, right? But when the angle between them is 90 degrees, then the cosine is going to be 0, okay? So this is one way, this is one thing that we expect to show up in our metric. We expect the cosine to show up in our metric. Okay, and we also know that the energy that I'm expending is going to be proportional to the force I put in and the distance that we want the block to go. So we can straight up say our metric should be equal to the magnitude of the force times the magnitude of the distance, and then scaled by this cosine metric, right? To indicate that if the force and distance are orthogonal, then we're not transferring any energy, we're not doing any useful work. And if they're parallel to each other, then we are doing the maximum amount of useful work, right? If they're in the same direction. Okay, so this is, of course, one way of writing the dot product, right? There's a couple other ways we can get to this conclusion as well. Fundamentally, what we're doing is we're coming up with a metric for similarity between vectors. We want to see how similar are two vectors to each other. Another way we could go about deriving this is using projection, okay? And in order to illustrate that, I'd like to show you guys a quick animation. So in this animation, we have two vectors and the projections of the two vectors onto each other, okay? And we're changing the angle between them. We see as we change the angle, the two vectors are becoming more and more perpendicular to each other, and both projections are getting smaller and smaller and smaller and smaller until they're 90 degrees and the projections are 0. And then the angle's increasing again, it's deviating from 90 degrees, so the projections increase again, okay? So now, how does that connect to the cross product? Well, this is I just drew out the vectors here and the projection. We know that the projection onto B of A, we know how to solve this. Okay, this is simple trigonometry, because this right now we've created a right angle triangle, and this projection of B of A, the magnitude of this is going to be equal to the magnitude of A, the A vector, times cosine theta. Why is it times cosine theta? Because it's times the adjacent length over the hypotenuse, right? Times adjacent over hypotenuse, and the hypotenuse is just equal to the length A, and the adjacent is this length that we want right here, okay? So then it becomes A times cosine theta. Okay, so this is the projection of A onto the vector B. The projection of B onto the vector A is going to be the projection of B onto the vector A is going to be conversely equal to this, B times cosine theta. But we want to figure out a metric that's symmetric, okay? So it doesn't matter if we're taking the projection of A onto B or B onto A. The metric that we want to get, we want it to be equal for both of them. So basically, we can just multiply this by B and multiply this by the magnitude A, and then we get the cosine again, okay? Or we get the dot product again. So and this represents how, as the vectors get more perpendicular to each other, their projections decrease because they're less similar to each other, right? And as they get closer and closer to each other, the projections increase because they're more similar to each other. And this metric is symmetric. It doesn't matter if we're projecting A onto B or B onto A. It's considering the length of either projection, right? The length of both projections is considered in this product. What about that other metric we have for dot product, the other formula we have for dot product, the element-wise formula? Where does this formula come from, and how can we understand this formula? Well, thinking back to that physics problem about work that we were talking about earlier, we can think of the dot product as quantifying directional growth. Basically, how much push does one vector give to another vector? And the way to quantify this is how much push is that the x-coordinate can only push the x-coordinate of the other vector, and the y-coordinate can only push the y-coordinate of the other vector. So that's why we're multiplying the same components of each vector. because we're applying one vector to another, and we're thinking about how each x component interacts with each x component and how each y component interacts with each y component. We can split this apart and look at this piece by piece, okay? So, for instance, we have a vector A, and we have another vector B, and we can split up these vectors into their components. So the A vector has this x component and this y component, and the B vector has this x component and this y component. Okay? And basically, we can say piece by piece, how does each component of this vector interact with each other component of this vector, okay? So if we're thinking as one being force and one being distance, how much of this force moves the block this distance, right? And how much of this force moves the block this distance? So let's go through it step by step, okay? So how much of this force impacts this force? You multiply the two magnitudes, right? They're both facing the same direction, so you multiply these two vectors. You do ax times bx plus how much ax impacts bx? Well, if we're thinking about this as force and this as distance, this force doesn't move any distance up. So this is going to be ax times by, and this is going to be equal to 0, plus we're going to have ay now, ay times by. Well, we know that if we have a force pushing up, then that's going to move the block a distance up. So that this component is not equal to 0. Ay times by plus, finally, we have ay times bx. And this component we know should be 0, because if we're thinking about how much directional growth A is applying to B, how much energy A is transferring to B, how much the force A is pushing the block a distance B, how much the force AY is pushing the block a distance BX is going to be 0, right? So when we sum this all up, it's just the only components that matter are AX, BX, and AY, BY. So basically, how do we think about dot product? We can think about it as a similarity metric, or a parallelity. I'm not sure if that's exactly a word, but a parallelness metric. We can also think about it as how much energy or push does one vector apply to another. And a good example of this was, mechanical work, which was a physics problem we were talking about earlier, which you might recognize from high school physics. Another example is, let's say you're swimming, and you're swimming a certain direction, and the current is some other direction. You want to line up the direction you're swimming with the direction of the current. Another sort of interesting example of dot product that I would quickly like to go over is, let's say you have a vector A, and this vector is used by a grocer. So to define the price of each fruit that he has, or each, let's say it's like $5 per apple, $6 per grape, and $3 per banana. And then, let's say we have number matrix B of what's on your shopping list. So, I don't know, let's say one apple 2 grapes and 3 bananas. How do you figure out how much money you spend at the store? Well, you have to do a dot product. You basically have to do dot product, right? You match up each element and you do an element-wise multiplication. We're ignoring how the price of a grape impacts how many apples you buy, right? Or how many apples you buy impacts how much you pay for grapes. Because those quantities don't make sense to multiply to each other, right? We only multiply quantities that are related to each other. So you can see how this ties back to relational or directional growth. How much one pushes another, right? How much these two vectors are similar to each other and the effect that the similar components have on each other, okay? So yeah, that's a quick explanation of dot product. If you have any questions, please let me know and feel free to contact me.